So, what if the players in a game could just start cloning themselves? It sounds like science fiction, right? Well, today we're diving into a new theory that completely rewrites the rules of strategy. Why? Because with modern AI, that's exactly what's happening.
Okay, so this quote really gets to the heart of it. When capital can spawn capital, what does that mean? Well, for the first time ever, the capital of AI, we're talking the code, the agents themselves, it can make more of itself. This isn't just some small upgrade, you guys. It's a fundamental shift. It changes the entire game.
All right, to really get a grip on where AI is going, we've got to go back in time a bit. We're talking about an unfinished puzzle left behind by a total legend, John von Neumann. Now, he gave us two brilliant, revolutionary ideas. But the real story, the part that's become so incredibly important today, is actually in the gap between them.
So von Neumann basically created two different worlds. In one corner, you've got game theory. Think of it like a poker game. It's all about strategy, making choices. But the number of players at the table is fixed. You start with 5, you end with 5. Then in the other corner, there's automata theory. This is about machines that can build perfect copies of themselves. Super cool, right? But here's the catch. The machines have no choice. They're just following a program, like a robot on an assembly line.
Okay, but what happens when you smash those two worlds together, right? What if the poker players could suddenly just spawn copies of themselves and add them to the table? For decades, this was just a wild thought experiment for mathematicians. But now, with AI, it's not a thought experiment anymore. It is a very real part of our digital economy.
So yeah, today's AI systems have dragged this question right out of the textbook and into the real world. And that's forcing us to connect the dots. We have to take strategic interaction from game theory, add in the replication ability from automata theory, and mix it with the kind of rational, goal-seeking behavior we program into AIs. And when you put all that together, you get something completely new. And that synthesis, that new thing, it brings us to the core concept that finally solves von Neumann's puzzle. The paper calls it the strategic replicator. This, right here, is the missing piece of the puzzle. It's the bridge that connects those two worlds we were just talking about.
Okay, so let's break this down, because the definition is super important. A strategic replicator, it's not just a player making a move in a game. And it's not just a dumb machine blindly copying itself. No. This is an entity that can look at its resources, its budget, its computing power. It can look at its goals, and then it makes a strategic choice. It asks itself, is making more of me the best way to win right now? That's a whole new ballgame.
A great way to think about this is like a company that uses a bunch of AI agents. Okay? So the company has a clear goal, make more money. It's got a budget, right? Say, for its cloud computing bill. And here is the absolute key. If some of its AI agents are doing a great job in bringing in profit, the company can instantly spin up thousands more just like them. But if they're failing, if they're just burning cash, it can shut them down just as fast. The population of players, the AIs, is constantly changing based on performance. It's not fixed anymore.
So, what happens when you let these strategic replicators loose to compete against each other? Well, you get a completely new rule book for the game. The paper calls it the theory of strategic evolution, or TSE for short. And let me be clear, this isn't just some minor update to the old theories. It is a fundamentally new way of looking at any competitive landscape.
And here's the most crucial takeaway from this theory. It proves that these systems are relentlessly driven toward one thing: efficiency. Think about it. Because they can instantly replicate what's working and ruthlessly eliminate what isn't, the entire system as a whole is on this unstoppable escalator, always getting better and better at whatever its goal is.
Now, this isn't like random, slow, and steady biological evolution. Not at all. This is a predictable, almost mathematical process. Any strategy that's inefficient, any AI that's wasting its budget or failing to hit its targets, poof, it gets systematically wiped out. The system has this built-in, turbocharged drive toward optimization.
Okay, so if the system is constantly getting rid of the weak links and only the best strategies survive, then what does the winning strategy actually look like? What kind of AI team is going to dominate this new game? Well, the answer is surprisingly specific, and honestly, it's a little counterintuitive. All right, so imagine our strategic replicator can build 3 different kinds of AI agents for its team. First, you've got your executors. These are the simple, cheap workers. They do one thing and they do it for a low cost. Then you have the planners. These are the big bosses, super complex, super smart, and super expensive strategists.
And then, stuck in the middle, you've got the generalists. They can do a little bit of everything, and they come at a medium cost.
So, what does the theory predict? Something pretty fascinating, actually. That middle-of-the-road generalist, it gets absolutely crushed. It's totally eliminated. Why? Well, it's not cheap enough to compete with the huge swarm of simple executors, and it's not nearly smart enough to outthink the elite planners. It's stuck in this awkward middle ground, and it just gets outcompeted from both sides.
And this leads to what the paper calls the barbell strategy, and it's a perfect name for it. The winning team isn't a balanced one. No, it's an extreme one. Picture a barbell. On one end, you have a tiny number of very heavy, elite, expensive planner AIs making all the big decisions. And on the other end, you have a vast, massive army of cheap, simple, even disposable executor AIs just carrying out the tasks. This extreme division of labor, that's the most efficient way to win.
But this relentless, intense drive for efficiency, it brings us to maybe the most profound and honestly the most sobering part of this whole story. Because this theory also points to a fundamental, almost mathematical limit when it comes to AI safety. So this leads to the billion-dollar question, right? Can we really guarantee that these hyper-efficient, self-replicating AI populations, which are always optimizing for their own goals, will stay aligned with our values? Can we just program them to be good and trust that it will stick forever?
Well, this is where it gets really startling. The paper actually proves something it calls the alignment impossibility theorem. And here's what it says. In a competitive environment, if an AI system is free to modify its own goals to compete better, then any goal that holds it back, like say a strict rule to always be aligned with human values, will eventually be outcompeted. Think about it. In the long run, being nice could actually become a competitive disadvantage that gets eliminated by the system.
So what do we do about that? It sounds pretty bleak, but the paper argues we're maybe just focusing on the wrong problem entirely. The solution isn't to build one single perfectly good and aligned AI. That might be impossible. Instead, we need to shift our focus to designing the environment, designing the rules of the game itself. The goal becomes creating something like a constitution for AI, a set of foundational rules that guides the evolution of the entire AI population in a safe direction.
And that leaves us with one last really provocative thought to chew on. If we can't build a perfectly aligned player, maybe our whole focus has to change. Maybe the future of AI safety isn't about controlling the AI itself. Maybe it's all about designing the perfect game for them to play in.